Yeah, so I'm connecting now both of my damaged inverters here on my bench. I will connect them both here via a safety circuit with a series resistance, which is a light bulb. This is now the first inverter which came from the phase 1 and which I told you it blew at the breaker. So I'm expecting a short circuit inside the inverter. Let's open our supply here, and yeah, you can clearly see we have a light bulb which is steady on, and the inverter itself, we have just some flickering on the display, and that's it. So in my opinion, this is a clear indication of a straight short inside the device here on the main power rail. Let's take the second inverter and see if there's anything different. So this one now is the inverter with the unknown fault yet. I also have connected it with my safety circuit. Let's open the circuit, and we again do have a steady light, but now on this one we have a display. So if you look, it's actually quite a normal display. Just the voltage is showing 84 volts. What does that mean? Well, of course, we have a voltage drop over our bulb here, and then inside the inverter it seems to be that there is not a short circuitry on the main rail, so that means the voltage can build up other than you saw before on the other inverter, which is clearly shorted. And yeah, so this inverter is completely different. Interesting to see this difference, and yeah, we will see then what we can do out of the knowledge we got from this experiment here. Right, I've opened now this inverter, which we don't know yet what happened to it, and yeah, it's already kind of visible. We have ant infestation, so all these small ants, they came into the inverter and have built a nest on several places. There's also some general corrosion on it. These ants, you see, they are on both sides. They're on both sides, especially on the AC IGBTs. I don't know, maybe they like electricity. What is attracting them just here to the AC side? I'm no expert in insects, but yeah, maybe because it's just so many there, it's just a matter of cleaning, and this could already fix this inverter. So I will take out the board and give it a clean up, then check for corrosion and maybe fix the corrosion issues, and then we can check if there is a short or anything else still given. Yeah, and that's the absolutely biggest disadvantage of devices like this. Everything was not 100% closed in these climates will be infested by insects and humidity, so it really doesn't make sense. So if you're ever planning to use something like this, don't do it when you live at places like me. But otherwise this inverter was never disassembled before. These small ends, they are just going everywhere and it sucks. I gave the inverter a blowout with high pressure air. It's clean now. I saw some corrosion here in the electronics area, which I wanna reflow some components there. Just use some solder. But let's just check, do some measurements. And if I go here, inverter AC input, L and neutral, it is giving me 91 kilo ohms. That is good. So I turned the board on the other side just to check our IGBTs here. And the IGBTs, if I check drain and source, we are OL. The other one has 72 kilo ohms. Why? So there could be, of course, that this one is now measuring some other components here on the AC input, and the other side is maybe on the high side or low side, and this one doesn't measure anything. But there's definitely no short. If I check with the gate to drain, gate to source, OL, so that's perfectly fine. Here I have 9 kilo ohms, so that is probably a pull down resistor. So it's a little bit different on those sides. The thyristors here are also showing in the mega ohms, but there's definitely no short here, which is good. What I want to do, I found out at my newer inverters actually, which failed, is that here we have the AC, we have these big inductors, and then there's also a capacitor there. And there I actually found out that they should have 470 nanofarads, but actually they're degrading quite quickly. So on all my inverters which have failed, the values have been already below 400 nanofarads. So what I'm going to do is I want to take those caps out, because I have replacement ones, just measure them, and then we can put them back in or replace by new ones. So these will be the two jobs: reflow some of these SMD components and replacing or just checking those capacitors. So I've just replaced two of the SMD resistors. They have been just beyond repair. And now removing those capacitors. Good, so they should come out now. But here it is, number one. As well here, some silicone sticking on it. And number two. This one is showing 266 nanofarads. So as I told you, this should be actually a 470 nanofarad. And this one 356 nanofarads. So they are already quite below the target value. So I have ordered this already last time. These capacitors here, and they are 0.47 microfarad. New ones, they should be the same size. and they fit perfectly. Instead of gray we have this time yellow ones. Yeah, and this is really something what's happening to all these inverters. And why is that bad? These capacitors are working together in tandem with these inductors, and they are smoothing out the AC. When those capacitors are going off value, it is actually throwing out the balance of this circuit here. So this could actually, in my theory, have been a reason why the AC has failed so many times on the other inverters, because maybe the transistors do have then a different job to do, a more difficult one. Anyway, when components do have values which they are designed for, that can only be good. That's it. Just remove the legs. And the AC circuit is as good as new. Yeah, now interestingly, if I am measuring again source and drain of the one in transistor, which initially showed 72 kilo ohms, now with the new capacitor I'm reading 360 kilo ohms there. So looks like that the capacitor was already quite at the edge of also failing, and if the capacitor would have failed and shorted, then you again of course have a problem on the AC side. After all the measurements and what we've done, I'm feeling confident that we can try the inverter. I still have it here on the safety circuit. Let's just check how it looks now, if there's anything a little bit different, like voltages on the display. And yeah, so the inverter came on just like normal before. We have now 88 volts shown, and voltage is too low. So I also have the DC power supply for this test. And now I'm going to plug it in just into the AC. Yeah, nothing happened. No bank. As you can see, we have absolutely normal indication on the display. 235 volts, starting voltage too low. And here, if you look our control circuitry, we have a blinking LED. That means the inverter is correctly connected to the AC. I will now start raising the voltage on the DC, and you can also see the DC voltage here on the display is starting to go up. Now it's 13 volts. Around 30 volts, the starting voltage too low disappeared. So now we have to wait for the inverter to start inverting and pushing into the grid. Finally, I was waiting for this moment so long. We had a success. I have set the inverter to output 20 amps, so that's around 1000 watts, and That's why it does not go higher. Still we have 500 watts import from that phase, but yeah, I don't want to stress it too much at the moment. So let's just see if it stays alive for a while. But yeah, this was the much needed success. The inverter got taken down by insects and corrosion, and this time it was sort of easy fix. Yeah, we are back on 2 running inverters, which is great because that's enough to use the Powerwall again fully. There's still one more inverter, so the SUN2000, which had 500 watts output but then blew up again. This will be another repair attempt. I had gained a little bit more experience, and yeah, so maybe this time we can fix it the way that it is, then also outputting a little bit more and stable power. That's it for this video. Thank you for watching. If you liked it, please like, comment and subscribe. I see you at the next one.